Foundations of Mathematics for Elementary Teachers. An in-service program designed to provide background for the improvement of instruction in mathematics in the elementary schools. Prepared by E. Glenadine Gibb and Augusta Schurer, members of the Department of Mathematics, State College of Iowa in Cedar Falls. Your instructor, Glenadine Gibb.
Suppose I live on an east-west road, and a friend of mine lives on that same road. I plan to visit my friend and ask you to join me. Since you know where I live, I tell you that my friend lives 5 miles from me. But you ask, 5 miles east or 5 miles west? To give you the number of miles was not enough. You also wanted a direction indicator. 5 miles east or 5 miles west. The thermometer is 35 degrees. 35 degrees above zero, 35 degrees below zero. Your weight has changed 10 pounds. Did you lose 10 pounds or did you gain 10 pounds? There are many situations that we can describe properly only if we have a number and a direction indicator. Our attempt to describe these situations leads us to consider the set of integers, numbers which represent both magnitude, that is, how much, how many, and also direction, which one of 2 possible choices. A mathematician calls a quantity which represents both magnitude and direction a vector. Our consideration of the integer then will enable us to denote vector quantities and also to give a more comprehensive answer to our question, what is a number? You recall that we use pairs of whole numbers to describe certain regions relative to a given unit region, or certain lengths relative to a given unit length. We use pairs of whole numbers to help us name fractional numbers. How can we use pairs of whole numbers to help us name the integers, numbers that we can use to describe in the physical world an amount of change and in what direction that change takes place? Let us think of a number line, such as the one that we have represented here. And we see here that this has been laid off in unit segments, several of them. Now let's think about selecting one point here, and we'll associate with that 0. And with this one, 1. We could have associated 1 over here. Our choice is arbitrary as to which direction we go. With this one, 2. With this, 3. With this, 4. With this, 5. Well, we'll stop here. Now let's think about a directed segment, such as one we have here. What pair of whole numbers could we associate with that segment? We see here that the head, indicated by this arrow direction, the head is at 3, the tail 1. We use the ordered pair 3, 1 to associate with this directed segment. Now if we use this matter of the head being associated with the first number of the pair and the tail with the second, let's see what we might do if our segment were like this. 1 equivalent in length to this, but opposite in direction. What pair would we use? The pair 1, 3, with the head, with the tail. Now we note here that the directed segments associated with these pairs are equivalent in length, but opposite in direction. We have used the arrowheads to indicate the direction in which we wish to think of these. But let's consider some other pairs. This time 2, 0, 4, 2, 5, 3. What directed segment or segments can we associate with these? We see 2, 0, 4, 2, 5, 3. A 2-unit segment in this direction, similar to the one we have associated with 3, 1. Let's consider the set of pairs. We'll call this set S, which then are represented by this directed segment. The property common to these pairs and all other pairs which are members of that set can be named using the symbol a positive 2. 2 units in a positive direction. Let's consider other pairs of numbers. 0, 2, 2, 4, 3, 5. With what segments can we associate with these pairs? 0, 2, 2, 4, 3, 5. Again, 2 units in this direction, or as we had for the pair 1, 3. Let's call this set, and all other pairs which are members of this set R, which represent this particular segment, 2 units in this direction. We name this property common to these pairs using a negative 2. 2 units in a negative direction. With the properties, the symbols, a negative 2 and a positive 2, then indicate or represent vector quantities. Both magnitude and direction are indicated. These new numbers represent vectors. But let's think of some other sets of ordered pairs. For instance, the set that we will call T. When we see here 5, 0, 7, 2, 8, 3, what property is common to this set, and how do we name it? We'll name that using the symbol a positive 5. Consider still another set, this time this set of ordered pairs, 0, 9, 1, 10, 9, 18, and so on. What integer can be associated with this set? A negative 9. Consider still another set, and this time 0, 0, 1, 1, 2, 2, and so on, and n. Let's use a representation of a number line here to think about this. 0, 0. We see the head and tail coincide as 1, 1, 2, 2, and so on. Here we have a segment of 0 length. And since the assignment does not have a unique direction assignment, the property common then to this set is their integer 0 expressed in this way. These new numbers, the integers, which can be represented by 0, a positive 1, a negative 1, a positive 2, a negative 2, and so on, are helpful in describing situations in which the quantity in question can vary not only in amount, but also in direction. Note these symbols, the plus and minus. They are not associated here with addition and subtraction, but rather to indicate the direction of the vector. Speaking of addition and subtraction, how can we define sums for pairs of integers? You recall when we thought about sums for pairs of whole numbers that we associated that with a union of sets of objects. When we thought about sums for fractional numbers, we associated sums with union of regions or lengths. We will use directed segments to think about the sum of pairs of integers. Suppose we think about a pair, this time a positive 3, a positive 2. With the first number, we will associate a directed segment, 3 units, and in a positive direction. With the second, another directed segment, 2 units, and in the same direction. We will think about their sum by joining in such a way that the tail of the second coincides with the head of the first. Their sum, then, is such that the tail of the first and the tail of the sum coincide, and the head of the second and the head of the segment associated with the sum. To think of it another way, the sum extends from the directed segment associated with the sum, extends from the tail of the first to the head of the second. We see here that we have a segment, 5 units, and in a positive direction. We can then say that a positive 3 plus a positive 2 is equal to a positive 5. Now, what would happen here if we would change the order? Instead of a positive 3, positive 2, think of a positive 2, a positive 3. Well, this would mean then that we would start first with a segment associated with the first number, and then a segment associated with the second, and we see that their sum is also positive 5. Or in other words, we could write this. The addition on the integers is commutative. Now, let's think of still another pair. And this time, let's think of the pair, a positive 2, a negative 1. As I remove some of these things, you might be thinking of how you could define that using directed segments. A positive 2, a negative 1. What segments will you need to start with? The first one, positive 2. The second would be a negative 1. In other words, an opposite direction here, starting with the head of the first, the tail of the second, in this direction. What about their sum? With the tail of the first to the head of the second are represented in this way. 1 unit in a positive direction, which we can associate a positive 1. Consider still another pair. This time we'll take a pair in which the direction is the same, but both a negative direction. And again, I'll let you start on this one. A negative 1, a negative 1. Well, first we have a negative 1 in this direction, associated with the first number of the pair. And we have another one just like that, associated with the second member of the pair. The sum then, from the tail of the first to the head of the second, 2 units in this direction, a negative 2. Let's suppose that we had 3 integers. How do we find their sum? Consider these 3. A positive 3 plus positive 2 plus a negative 1. We could group these to think this way so that we really have then a positive 5 plus a negative 1 or a positive 4. But suppose we grouped in this way. We see then that we have a positive 3 plus, and here we have a positive 2 plus a negative 1, a positive 1, or a positive 4. This is an example which would indicate that the addition of integers is associative. But again, let's consider other pairs of numbers. This time, let's consider a pair where one of them is 0. A positive 3, 0. Again, we associate with the first this directed segment. 3 units in that direction. What do we associate with this? Recall that this 0 is associated with a segment which does not have length. In other words, its head and its tail is right there. So the product then could be expressed in this way, the sum as saying a positive 3 plus 0 is equal to a positive 3. Or if we wanted to use a directed segment associated with the sum in this. We see here that if 0 is one of the numbers, then the sum is the same as the other number. 0 is the identity element for addition of integers. Consider still another pair. And this time, let's take a pair where the length or the magnitude is indicated as the same, but a difference in direction. You might think of what's going to happen here. Positive 3, a negative 3. We start with the head, tail over here in this direction. Now our sum goes from the tail of the first to the head of the second. We would indicate that segment of no length here and associate with that the number 0. Or we write here a positive 3 plus a negative 3 is equal to 0. You recall when we found the product of two numbers, we found that in some cases their product was 1, the identity element for multiplication. We call those pairs of numbers multiplicative inverses. Here we see that we have pairs of numbers whose sum is the additive identity. These numbers are additive inverses. Let's consider some other numbers. What's the additive inverse of negative 3? That would be not a negative 3. We've been talking about 3s. Negative 5, a positive 5. Or of a positive 1. The additive inverse would be a negative 1. 0 would be 0. Every integer has an inverse. Now, suppose that we sum up what we have observed here graphically and see what has happened. The pairs of numbers and their sums. When the pairs had the same, indicated the same direction, we see that their sum also had the same direction and that the magnitude was really the length associated with the sum of the lengths, 3, 2, 5. Likewise, we had when they were both in negative direction. The sum, negative direction, and the magnitude, the sums here, 1 plus 1. was not so easy when we had opposite directions, a positive 2, a negative 1. We see that the sum, the magnitude here, is the difference of these two numbers. The direction is the sum of the direction of the greater. Again, if 0 was one of the numbers, the sum was the same as the other number. If the two had the same magnitude but opposite in direction, their sum was 0. Now we can identify sums in other ways, way in which we make use of this additive inverse. Suppose we consider the pair a negative 2, positive 5. We can express this by writing negative 2 plus a positive 5 is equal to the sum that we want to find. Let's rename a positive 5, rename it in such a way that we have 3 numbers, 2 of which are additive inverses. In other words, I'll choose to name this a positive 2 plus a positive 3. Another way of thinking about a positive 5. Now, using the associative property, a negative 2 plus a positive 2, we could then this 0 plus a positive 3 is equal to our n, or, as we see here, n would be then a positive 3. By renaming one of the numbers so that we have the sum of 3, then we can have a way of computing the sum for 2 integers. You also recall when we were considering differences for pairs of numbers, like say 5, 2, we were able to make statements like this. 5 minus 2 is equal to n, or to write that 5 is equal to 2 plus n. Thinking in this way, can we define what we mean by a subtraction assignment for the integers? Let's see. Suppose we consider the pair a positive 5, a negative 2. Now, if we think then, we would think of positive 5 is equal to a negative 2 plus n. Positive 5 then is associated with a segment which we will think of as being representing a sum. A positive 5 units here in that direction. A negative 2, one of the addends, would start here, and negative 2 in this direction. The other addend then must go from where? The head of this over here to the head of that. In other words, we would see that this would be 7 units in that direction, or a positive 7. We could then write a positive 5 is equal to a negative 2 we want to go back to our subtraction sentence now. A positive 5 minus a negative 2 is equal to a positive 7. Suppose we consider another pair. And this time, well, let's let the pair be a negative 2, positive 3. I'll let you start on that one. How do you think you can define this subtraction assignment? A negative 2, a positive 3. We can write this equation. A negative 2 is equal to a positive 3 plus n. This we will associate then with this segment. It's a negative 2. 2 units, and in this direction. The positive 3, well, it again will start with the starting point here and in this direction. What segment do we associate then with this number? Where must it be? We'll start with the head of this and go to the head here. In other words, we can use this to help us think about it. 5 units in this direction. We can write then a -2 minus a +3 is equal to a -5. Again, we have been defining differences graphically. Let's see how we might think about this by using another means. And shall we consider here the pair -8, +3. Let's write our sentence here as we've done before. A -8 is equal to a +3 plus n. Now we can also say by that that 0 plus a -8 is equal to a +3 plus n. Again, we can express this a different way by writing that we have a +3 using additive inverses here, a +3 plus a -3 plus a -8 is equal to a +3 plus n. The sum of these two is 0. Now, using the associative property, we see then that we have n must equal a -3 plus a -8. Or we can write here that n is equal to a -11. Consider our pair again, a -8, a +3. We see that we can find their difference by adding to the first number the additive inverse, in this case a -3, of the second. In this discussion, we have found that we can always assign a sum to a given pair of integers. We found that this was also true for the whole numbers as well as the fractional numbers. We also recall that subtraction was possible for the whole numbers and the fractional numbers when we had only certain pairs. Those pairs where the first member was greater than or equal to the second. For the set of integers, we see that we can assign a difference for every pair of integers, a difference which is another integer.
Foundations of Mathematics for Elementary Teachers has been presented by State College of Iowa under a grant from the National Science Foundation and prepared by E. Glenadine Gibb and Augusta Schurer, assisted by E.W. Hamilton and Diane Baum. The program was produced and directed by Robert Gabler and recorded at KDPS in Des Moines, Iowa.